Hello, my name is Grant Helm, and I'll be presenting my results and my analysis for Lab 11. It's an extension on Lab 3, the beam vibration. I'm performing it on overhanging cantilever beam. A little bit of background for this. Above is pictured the standard cantilever beam. Below is my version of the beam that I used for this lab. So I wanted to test different boundary conditions, and the different boundary conditions that I tested was adding a pivoting support at a certain point along the beam. And I wanted to see how that would affect the vibrations and the spectral analysis, the different frequencies and the modes of frequencies that this beam had. So my test setup included one ruler clamped between on one end, just as in Lab 3, and then a second support between two markers. And then I had a clamp sandwiching both of those things tightly. That's a little bit difficult to set up, but it did work out in the end. I had the same Wheatstone bridge circuit, collecting my data, sending it to the MSP board, sending it to the high-speed data collection setup, and then interfacing with GUI. So very similar to Lab 3, just with an added support. My experimentation, the first step, just as in Lab 3, I displaced it with an initial displacement of about 20 millimeters, and then I released it while collecting data. So I waited about 0.8 to 1 second before releasing it. And the rest of those 7 seconds or so, 6 or 7 seconds, was a collection of the vibration data. And then I did the same with an impact, just as in Lab 3, find a small weight and drop it from a height onto the end of that beam or ruler and see how that vibration behaves. I collected 3 trials for each of these data sets, or each of these modes of data collection. So I ended up with 6 data sets in total. For my data analysis, I plotted all the data initially. I chose the best of those 3 for each of the cases. So I ended up with 2 data sets at the end. I trimmed each of those data sets to the point where the vibration started, the free vibration happened, and that allowed me to run a spectral analysis on each of those data sets. It's important to note that I didn't convert these data sets into displacement form as just voltage. I didn't have the correct conversion from voltage to displacement because the sensitivity was different because of the beam parameters were different. So that's important to note. My results, it appears that there's a lot more noise. Go back, a lot more noise in the signal. It also appears that there is more damping, although because the voltages are smaller, it might be that the noise is interfering with the decay, and it's actually not as high of a damping as it appears, and it continues to taper, but the noise is interfering with it. It's a possibility. I do believe that there is a lower sensitivity on this beam because more of the bending moment is distributed across the beam. And that's why we're getting lower voltages at that initial displacement. And if you could see, if I pictured that data from the beginning, you would be able to see that. But similar results here. I'll move on from this to the spectrum analysis. And this is where it gets interesting. It's because my first mode of vibration for the overhanging beam is 30 hertz, and the first mode of vibration for the standard beam is 13. So a lot higher standard or first mode of vibration in the overhanging beam. And that's expected because I've shortened that, basically vibrating the length where that first mode of vibration occurs. And a shorter length, as we all know, produces a higher frequency. So that checks out. I have a similar analysis for the impact vibrations, but the results are very, very similar. Thank you for your time. I hope this was interesting.